Have you ever tried to, say, machine something really precise, maybe super small and thin, like for a medical device, and you watch it just bend or vibrate or chatter under the tool? It just turns into scrap. It's incredibly frustrating, right? But it's also a huge multi-million-dollar headache in manufacturing. Costs a fortune in time and materials. Well, today we're doing a deep dive into this amazing bit of engineering that basically just solves that exact problem. It's called the Swiss-type lathe. It's kind of the quiet hero behind some of the tiniest, most perfect little parts that make our modern world tick. So our mission here is to really pull back the curtain on how it gets that incredible precision. We'll look at how it's fundamentally different from, regular lathes. We'll explore the genius behind its main parts and why it's just essential for industries that need tiny, perfect components. By the end of this, you'll have a really solid grasp of this fascinating tech. Let's jump in. Okay, so when I was looking into this, one thing kept popping up again and again, this idea of the workpiece moving through something called a guide bushing. For anyone not familiar, why is that specific detail so important right from the start? What makes it the key to understanding what a Swiss-type lathe actually is?
Yeah, that's really where the whole concept begins. It's the core idea. This design, it's specifically engineered for making long, thin, often complex parts, lots of them, and typically all in one go. It directly tackles those vibration and bending issues you mentioned, the ones you always fight on conventional lathes where, the part just sort of whips around when you try to cut it. The fundamental difference, it's simple but profound. On a regular lathe, the part gets clamped, it spins right there, and the tools move along it. But on a Swiss type, the bar stock itself actually slides out past the tools. That change, moving the material instead of just the tools along its length, that's the secret sauce. That's where the precision comes from.
Okay, the material sliding through versus just spinning in one spot. That really does sound like a fundamental shift. Can you paint a picture of how that changes the actual physics, when the tool meets the metal? Especially thinking about forces and keeping things from bending compared to a standard lathe.
Oh, it completely changes the game. It's a totally different way of thinking about controlling the material during the cut. See, with a conventional lathe, you clamp the material in a chuck, right? And it spins. The tools travel along the z-axis, the length. So the further the tool gets from that chuck, the less support the workpiece has. And that's when you get vibration, deflection, especially with long, skinny parts. They just want to bend away from the tool. Now, with a Swiss type, because that material is sliding through the guide bushing, the cutting point is always super close to the support point, right there. The tools mostly just move in and out, X and Y axis, cutting the material as it emerges. And this brings us to a really crucial piece, the headstock. On a regular lathe, the headstock, the part that spins the material, is fixed in place. But the Swiss type has what's called a sliding headstock. It moves along the z-axis, pushing the material out.
Ah, okay, so the z-axis movement comes from the material being pushed, not the tool traveling along it.
Exactly. That one design change just opens up a whole world of possibilities. It's why Swiss types often have way more axes, like 7 to 13 axes are common. This lets them do multiple things at once, turning, milling, drilling, tapping simultaneously.
Wow, 7 to 13 compared to what, 3 or 4 on a conventional lathe?
Right, and conventional lathes usually do those operations one after another, sequentially, much slower for complex parts. So this also dictates what each machine is best for. Swiss types absolutely excel with those long, slender, complex, tiny parts. Conventional lathes, they're better suited for shorter parts, maybe with larger diameters. And one more thing, coolant and finish. Swiss types almost always use oil-based coolants.
Why oil?
Better lubricity, better heat removal right at that intense cutting zone. And this often gives such a fine surface finish, you might not even need any secondary polishing or grinding. The part comes off basically finished.
That's a huge efficiency gain right there.
It really is. Conventional lathes often use water-based coolants, and you frequently need those extra finishing steps afterwards.
That sliding headstock, it really does sound like the core innovation here. Most people probably think of z-axis motion as the tool moving along the part. Can you break down a bit more how the material moving forward changes everything for precision and complexity? I know it sounds technical, but it feels like that's the real heart of this machine.
It absolutely is the heart, no question. Think of the sliding headstock as a very precise, movable collet chuck, a clamp that holds the round bar stock very accurately. Its whole job is to grip that raw material bar and just meticulously push it forward through the guide bushing right past the cutting tools. So yeah, the main z-axis movement you see, that's the material advancing, not the tools traveling down the part's length. And this allows for something called segmented machining.
Segmented machining, okay, what's that?
It's brilliant, really. Instead of thinking about machining one long, wobbly part, You think about machining tiny, perfectly stable segments of that part, one after the other. So the headstock pushes out just a small length of the bar through the guide bushing. The tools machine just that little section, which is rigidly supported right there. Then the headstock advances the next small segment, and the tools machine that. Repeat, repeat, repeat.
Ah, I see.
So the machine is always cutting material that's fully supported right where the action is happening. That distance from the support in the guide bushing to the cutting tool edge, it basically never changes, even if the final part is, say, 100 millimeters long.
Wow.
And that's what eliminates the vibration. That's what allows for incredible precision on these long, thin features. Honestly, I've seen projects that were just impossible on conventional machines, just making scrap, put on a Swiss-type, and suddenly you're getting perfect parts every single time. It's almost like magic sometimes.
That makes perfect sense now. So as you describe the segmented machining, it's like, okay, maybe a weird analogy, like trying to slice a really long, thin loaf of bread, a baguette maybe. Instead of trying to cut the whole wobbly thing at once, you're only ever cutting a small bit right where your other hand is holding it perfectly steady. Is that kind of the idea?
That's actually a fantastic analogy. Yes, you've nailed it. That's exactly the principle. Perfect support right at the cut.
Okay, cool. So if the sliding headstock is the heart, the engine pushing things forward, there has to be another critical piece working with it, right? The thing providing that steady support you keep mentioning. What gives it that absolute rigidity right at the cutting point?
You got it. If the sliding headstock is the heart, then the guide bushing is, well, it's got to be the soul of the machine. Think about trying to write, pressing down hard in the middle of a long, skinny pencil. What happens?
It bends or snaps.
Exactly. The guide bushing stops that from happening to the workpiece during machining. It's essentially a very solid, ultra-precise sleeve that provides support literally right where the tools are cutting, millimeters away. This is what stops that long, thin workpiece from bending or vibrating under the pressure from the cutting tools. And that's absolutely crucial for accuracy, especially when you have parts with a high length to diameter ratio, much longer than they are wide. Anything over maybe 4:1, it becomes critical.
Okay, so it's a super precise support sleeve. What else does it do?
Well, its role is really threefold. First, yes, positioning and support. It's made of super hard material, ground to incredible tolerances. The inside diameter matches the bar stock diameter perfectly. We're talking clearances maybe as tight as 0.003 millimeters.
Wow, that's tight.
It has to be to ensure the workpiece is perfectly centered and simply cannot bend when the tools push against it. Second, and this is clever, synchronous rotation. The guide bushing doesn't just sit there. It actually rotates.
It spins with the part.
Exactly, at the exact same speed as the main spindle spinning the bar stock, usually driven by a synchronous belt. This is vital. It prevents friction between the rotating bar and the stationary bushing, which would cause heat, wear, and possibly twist the material. Ensures a smooth feed.
Okay, that makes sense. Prevents binding.
Right. And third, because you have this incredibly rigid support right at the cut, it allows for deeper, faster cuts. You can take much more aggressive passes, remove more material in one go without worrying about the part deflecting or vibrating.
Unlike on a conventional lathe where you'd have to take tiny little cuts.
Precisely. On a conventional lathe, you'd be forced into multiple shallow, slow passes to avoid bending the part, much less efficient. The guide bushing lets Swiss types be both incredibly fast and incredibly precise. It really pushes the limits of what engineers can design and manufacture efficiently.
That's a really clear picture of the mechanics.
Yeah.
Amazing stuff. So let's zoom out a bit. Thinking about the bigger picture, who really benefits the most from these incredible machines? Where are they making the biggest impact in the real world?
Well, you take those core strengths, right? High precision, the ability to make tiny things, and highly automated production. And you immediately see why they became absolutely essential in several really demanding industries. I mean, arguably, the Swiss-type lathe didn't just make manufacturing better. It actually enabled the whole miniaturization revolution we've seen. It allowed engineers to design things they simply couldn't make before.
Like what kind of things? Which industries?
Okay, think about medical devices. This field needs absolute perfection. Parts often go inside the human body. We're talking orthopedic implants, bone screws, tiny components for pacemakers, miniature surgical tools, even microscopic needles. They need micron-level precision, often made from really tough materials like titanium or special stainless steels. A Swiss type can machine these incredibly complex parts, sometimes with multiple features, all in one setup, one clamping. That dramatically boosts the quality and the yield rate. Fewer bad parts. critical for safety and cost.
Makes sense. Critical parts need critical manufacturing. What else?
Then there's electronics and communications. Our whole connected world runs on unbelievably tiny connectors, pins, sockets. Think about components for 5G infrastructure, fiber optics, the connectors inside your smartphone. They need to be mass-produced, millions of them, with perfect consistency. The speed and rigidity of Swiss-type machines mean that the millionth part is identical to the first. That guarantees the reliable performance we all just expect now.
Right, the tolerances must be incredibly tight for those high frequencies.
Exactly. And then aerospace and military, they also rely heavily on Swiss types, often working with really difficult-to-machine materials, titanium alloys, Inconel, things like that. You find Swiss machine parts in critical systems like navigation instruments, fuel injection nozzles for jet engines, actuation systems. Again, it's about complex geometry, high precision, and absolute reliability. These machines can perform multiple complex operations while keeping errors from adding up. Failure in these applications is just not an option.
So medical, electronics, aerospace, any others?
Oh yeah, plenty more. The watchmaking industry, of course, given its origins in Switzerland and the need for tiny, perfect gears and screws. The automotive sector uses them for fuel injectors, sensor components, small shafts. Also, firearms manufacturing for intricate components. Even high-end musical instruments sometimes use small, precision parts made on Swiss types. Basically, anywhere you need small, complex, high-precision parts, often in high volumes, you'll likely find Swiss-type lathes doing the work.
So there you have it. It really sounds like Swiss-type lathes with that unique sliding headstock and the absolutely essential guide bushing. They really are these sort of unsung heroes of precision manufacturing. They're making these tiny, incredibly complex parts that, well, that really underpin huge parts of our modern world, making them not just possible, but making them perfect. So maybe the next time you pick up a device with tiny, intricate parts could be a medical tool, a connector in your phone, maybe even a piece inside a fancy watch. Take a second to think about the hidden engineering that went into making it so flawless. Think about how one seemingly small design idea, just supporting the workpiece right next to the cutting tool, how that led to such monumental leaps in what we can actually build. And how precision, quietly shapes our daily lives in ways we probably don't even realize.